So as I was saying at the end of the last video, um, as you do your practice problems with these, if you're using the equation for when the charge is being brought into a field, FQ over E, then if that charge is positive, the direction of the field and the direction of the force will be the same. If that charge is negative, then the direction of the field and the direction of the force will be opposite. If you're using the equation where the Q is the source of the field, the central object, then the field will, for a positive charge, always be going outward, and for a negative charge, it'll always be going inward. Okay, so the first few questions tonight with these two are pretty straightforward. But then what happens is this stuff. When you have two charges that are close together and their fields overlap. And so I'd like to do an example with you of this because you're going to have two of them, I think, this evening. So I'm going to do one that's actually harder than the two you'll have this evening. And that way life should be, the two you have this evening should be easier. So it's question number 28 on page 655. And so it says you have a charge at point A of negative 12 microcoulombs. You have a charge at negative 12, I think it is. Let me just double check that. Yeah, a charge at point B of negative 15 microcoulombs and a charge at point C of positive 8.1 microcoulombs. We're told that A to B is 18 centimeters, B to C is 24 centimeters, so you can find A to C, and this should be a 3, 4, 5, so this should be 30 centimeters. And that means this angle is going to be 36.87, and you can do sine and cosine to find that if you don't believe me. So the question wants to know, though, what will be the field at point D from these three charges? Right? So again, this is, I'm going to write it as 0.18, just so we remember to change, and this will be 0.24 and 0.30. So the first step is to find the field at D from A, and then the field at D from B, and the field at D from C, the same way we did it with the forces. So EA will be equal to KQA over R squared, and EB will be equal to KQB over its R squared, and QC will be equal to KQC, over R squared. So 9 times 10 to the 9th Newton meters squared per coulomb squared. QA is negative 12 times 10 to the negative 6. And I'm not going to move my decimal right now. I'll just type it in my calculator as negative 6, and it will be able to cope. And then my R was 0.24 meters. And remember, that's squared. For this guy, 9 times 10 to the 9th Newton meters squared per coulomb squared. B was negative 15 times 10 to the negative 6 over, and this one was 0.30 squared. And C, 9 times 10 to the 9th Newton meters squared per coulomb squared, positive 8.1 to the negative 6 over 0.18 squared. So this should be reminding you of the same thing we did with the forces. The only difference is the point where we're trying to find the net field doesn't have a charge in it because we don't need, like, it's just KQ over R squared. We don't care about what charge is here. We're just looking for the strength of the field. Okay, so do the math with these. And for the first one, you should get 1.875 times 10 to the 6th newtons per coulomb. Oh, I forgot to talk about that. What is field measured in? So the coulombs here are one coulomb's going to cancel. The meter squared's going to cancel, and it's going to leave you with newtons per coulomb. And this one's going to be a negative. This one's also going to be a negative. 1.5 times 10 to the 6th newtons per coulomb. and this one's going to be a positive 2.25 times 10 to the 6 newtons per coulomb. Okay, so now we have our fields. I'm just going to move point D down here so we can look at it more closely. So A, the negative is simply saying that the source is a negative charge, and if the source is a negative charge, remember then the field lines are going into it. So the field lines around A are going in, which means this field line from A that's passing through B is going into A. So this is going to be EA, which was 1.875 times 10 to the 6 newtons per coulomb. And I dropped the negative on purpose this time because all the negative was doing was telling me that that field line was going into the source. B is also negative, which means it's also going, the field lines are going into B. So all the field lines around B are going inward. And so the field line that's passing through D to C is going down like this. And it is 1.5 times 10 to the 6 newtons per coulomb, and that's EB. Now C is positive, so we know the field lines around a positive charge go outward. And so the field lines from C that's passing through D is actually going up. So this will be EC, and it's 2.25 times 10 to the 6 newtons per coulomb. So when you draw these field lines in, once you use the positives and negatives to figure out the directions, you drop the positives and negatives. Now we need to find the component of our EB. So I'm going to draw my thing here. So this will be my EBY, and this will be my EBX. And yes, you could have drawn it up like over first and down. I just didn't because my EA was there. So this angle should be this angle, okay, which means 24 over 30, so it should be 53.13. I think I did that right. I'm just double checking now, right, because it's opposite. It's the same as that one. Yeah. Okay. So EBY then should be 1.5 times 10 to the 6 newtons per coulomb cos of 53.13. And when you do that, you should get, cos is 0.6, you should get 9 times 10 to the 5th newtons per coulomb. And EBX should be 1.5 times 10 to the 6 newtons per coulomb sine of 53.13.8. So this should be 1.2 times 10 to the 6. Now, if you drew your triangle the other way, you'll still get the same values. You'll just have sine instead of cos because you'll be using 36.87. All right, so now we do sum of the fields. Sum of the fields in the x direction. So we have two fields both going in the x direction, and they're both going the same way. So we're going to add them up. 1.875 times 10 to the 6 newtons per coulomb plus 1.5 times 10 to the 6 newtons per coulomb. And that's going to give us a total in the x direction of 3 point, did I screw this up? I hope not. Oh, sorry, x is 2, that's why. It's like I can't add 1.5 and get 3. 3.075 times 10 to the 6 newtons per coulomb, and it's going to the left. Okay, and then I do sum of the forces in the y direction. One's going up and one's going down. So 2.25 times 10 to the 6 newtons per coulomb minus 9 times 10 to the 5th newtons per coulomb. And that's going to give me 1.35 times 10 to the 6 newtons per coulomb. And it's going up. Okay, so now I think it's going up, right? C was pushing away. Yeah, so now I draw my thing. So I have one going up, 1.35. I'm going to run out of time. The other going over, and then do Pythagorean theorem. Okay?